Good afternoon to all of you. Welcome to the live session 2 of the course Reagents in Organic Synthesis. So there are few questions that was asked, so I will solve now. So one question was about hard and soft nucleophiles and electrophiles. So the attraction between nucleophiles is governed by the two factors. The first one is the electrostatic attraction between positive and negative charge, or dipoles. And the second one is the orbital overlap. Between the HOMO of the nucleophile and the LUMO of the electrophile. And which factor dominates? That depends on the hardness or softness of the nucleophile electrophile. Now I will discuss some examples and definition. So nucleophiles containing small electronegative atom and if you see this small electronegative atom, that is there in the early rows in the periodic table. Such as oxygen or fluorine or chlorine tend to react electrostatic control. So they are hard nucleophile. On the other hand, nucleophiles containing larger atoms and they are later rose in the periodic. So they tend to react predominantly under control of orbital overlap and they are soft nucleophiles. So we can see some more examples. F minus, OH minus, OR minus, SO42 minus, Cl minus. Borderline is azide, cyanide, and soft is I minus, RS minus. So from this also you understand they are small and also they are quite basic. So they are basic and they are not so basic. Also neutral molecules like H2O, ROH, ether, ketone, they are hard because they have the oxygen atoms, and these amines are borderline, primary amine, secondary amine, but thiols they are soft, and this phosphine also NH3, RMGBr, RLI. This is the negative charge on R minus because they are highly polarized. So this is also hard nucleophile. So alkenes, aromatic rings, they are also soft nucleophiles. Now we will see the electrophiles, hard and soft electrophiles. And the obvious choice is the H plus. So H plus is a very hard electrophile. So Br2 is a soft electrophile because its orbitals are large and diffuse, and also it is uncharged. So electrophiles and nucleophiles which are small, charged and not polarizable, those are called the hard, and those which are large and can be easily polarized, they are called the soft electrophile or nucleophile. So we can see by one example, like alpha beta unsaturated ketone. So all of you know this bond, it is a polar bond. So because this oxygen is electronegative, so there will be delta minus charge on the oxygen and delta plus charge on the carbon atom. And this bond is not polar bond. So this is a covalent bond. And here the dipole is not so strong like carbonyl. So what will happen? The large dipole is formed here, and electrostatic attraction, because this delta plus charge is generated at the carbon atom, it's greatest at this carbon atom. So hard nucleophiles, and you know like common are RNGBr, RLI, these are very popular reaction, Grignard, RLI, they try to attack here. So suppose R dash is there, then you get this. This one. And now if you add soft nucleophiles, and for soft nucleophiles it attacks at this position, and of course this conjugation will be there. So why at this beta position? Then you have to see the LUMO. So if you see the LUMO of this double bond, so the orbital coefficient is large at this beta. If you see, this is the alpha carbon, this is beta, so the orbital coefficient is high at the beta carbon. So what will happen if we add soft nucleophiles like you know this cuprate, they are also R dash to cuprate, also thiol, they try to attack at the beta carbon. Suppose if you do a conjugate addition with cuprate, you get this product. So this alpha beta unsaturated ketone is a nice example. They have the two center, the carbonyl carbon, that is the electrophilic center. There the hard nucleophiles will react, and in the double bond this beta carbon, because they are the orbital coefficient is high for the LUMO, so the HOMO of the nucleophile, soft nucleophile will react at the beta carbon. So this is called the conjugate addition. Conjugate addition or 1,4 addition, and this is called 1,2 addition. So 1,2 addition case, you get the addition in the carbonate. Another question was asked about this 4-tarbutyl cyclohexanone. So in this 4-tarbutyl cyclohexanone, if we add the methyl lithium, then this equatorial attack, that is the measure that you get around 65, and the axial attack you get 35%. And if you add a CH3Li plus lithium chlorate, then this suppose AB, then you get 96%, and B you get around 4%. So we'll discuss why this selectivity. So what happens, this methyl lithium when adds to this ketone, this size will increase because you will see this coordination of the solvent. So what happens, and this coordination from the solvent with the lithium, so this size will increase, and that's why equatorial attack is more. So in this case you get A, and for the axial attack so you understand there will be some interaction with this axial hydrogen and this methyl, because this coordination is there, so you get B less amount. B is 35%. Now in the lithium chloride condition, this lithium chloride is additive, then this one gets increased. So the size and here you can see this 6-membered transition state is formed, oxygen, lithium, chlorate, and this is methyl lithium. So this methyl lithium coordinates with the chlorate, and this oxygen coordinates with the lithium, so you get a 6-member ring, and then this bond formation happens. So methyl adds from the equatorial side, and because of this increase in size compared to this 4-member, the 6-member is more bulkier, so you get here high selectivity, 96%. And for the equatorial case, axial addition, we can see the transition state CH3 Yeah, here you can add solvent also. So what will happen, because of this bulkiness, the interaction between the axial hydrogen will be more. So this will be very less stable. So that's why it is formed in very minor quantities, only 4%. So this also we can see in hydride addition. Like sodium borohydride or lithium aluminum hydride. So what you will get? In this case, you get the axial attack measure. So hydride comes from the axial side, you get 86% or sodium borohydride. And for lithium aluminum hydride, it is almost similar, 90%, little bit high. Very. So these phenomena all are kinetic phenomena only. That also we can understand if we put the substituents here, that I will show in a minute. But here you can understand that this BH4 and ALH4, they are not so bulky. Okay, because ultimately this hydride comes from this another bond is there, hydrogen and boron. So that hydrogen does not have so much, because of the small size, does not have so much 1,3 diaxial interaction like earlier this lithium species like methyl lithium, phenyl lithium. So here you get this axial addition product is major, and this control that if we put now methyl substituents at this position, then you can understand the desired selectivity you don't get. So like this one, this already I think I have the PPT class. So there. So in this case you get only 48%. This clearly tells that now if you put a methyl substituents in this axial orientation, then what will happen? Then this interaction, this hydride whatever, this interaction is quite reasonable, because this interaction earlier it was between two hydrogen, now one methyl and hydrogen, so that's why you get only 48%. So earlier it was 86% or 90%, now it is 48%, and you get this one equatorial attack 52%. So that has become major now. So some question. So Kumar CH asking, please show the mechanism of conversion of cyclohexanone to cyclohexenone. I think this is very easy. You can see Segusa oxidation mechanism is already is there in the class. And Madan Kumar is asking if C double bond C is there instead of C double bond O, and we do oxidation with MCB in epoxidation and occurs on equatorial side. Yeah, that also can explain. So that and you know this epoxidation mechanism, right? So this is the electrophilic epoxidation. And this double bond will attack this one. So that's why, because of this large group, you get equatorial epoxide. So it depends on the group which you are bringing. So when you bring the large group, then you will get this equatorial. Because axial side, this group will coordinate with this hydrogen when it is axial. Okay, some more questions. Was asked about double Reformatsky reaction. So if you use excess of the reagent like this zinc, if this is 5 equivalent, and it has been shown that if you use now a base like TMADA, tetramethyl ethylene diamine 2 equivalent, and THF 50 degrees centigrade, then you get the double Reformatsky reaction. So this is delta hydroxy beta keto ester. So what could be the mechanism? And here it has been shown that both aldehydes and ketones can be reacted. So we just discussed the mechanism with benzaldehyde. So all of us know that zinc is a Lewis acid, so it will coordinate with to this oxygen as well as the carbonyl, and this ethylene diamine will coordinate with the zinc. So now this ester carbonyl also getting activated. So what will happen if you have a excess this reagent? Then you get another addition to this carbonyl. So you see this zinc is coordinated with 3 oxygen, 2 zinc is coordinated with 3 oxygen, and this you can first think of the enolate, the carbonyl, because this is quite acidic. So after aqueous workup, aqueous acidic workup, you will get the alcohol and your ketone. So that means this product is formed stoichiometrically by 2 equivalent of this reagent, but in reality you have to use the 5 equivalent of this reagent. Okay, another question was the anti-Markovnikov of Walker oxidation. And this we discuss in the class, that if you have the olefin and if you do the normal Walker for this terminal olefin, you get this ketone, methyl ketone in the Markovnikov. And this is the anti-Markovnikov. So in general, by Markovnikov, we know that how this product formed, that is the carbocation and this middle one, getting carbocation. But here, that means the terminal carbon, the carbocation is generated. So there will be two possible region. So one region for abnormal, one region the steric region. For the steric region, the normal is not possible. Normal. And another one is the stability. non-classical carbocation. This already we discussed in the class. So here uh, this intermediate forms, and the first case the sterics, because of the sterics it cannot attack. Suppose here so much steric is there, nucleophile cannot attack. Or the second case, there it is attacking at this terminal, and this carbocation, this is stabilized by other groups. And by other groups I want to say that long distance sigma or pi bonds. So that is the non-classical carbocation stability. So if the carbocation is generated here and that is stabilized by long distance double bond or long distance sigma bond, that is also possible, then you can get the anti-Markovnikov addition. So in the class I think we already discussed that if you have this diol and they have also an alcohol, this is MPM, and this one gives the Markovnikov product. And now if you protect it, so what happens when you doing the protection, then what happens, the steric is increasing. It is actually this benzyl CH2 methoxybenzyl. So now if you do this protection, then what will happen, then you get the aldehyde. So this is the steric. Now we will discuss this one, non-classical carbocation, one example. This is the worker condition. Here you get this one, this terminal olefin without substrate reacting, and it is reacting at the terminal carbon. So what happens here, these two methyls are good for the Tropignol effect, so that cyclization will be good. So now the first coordination will happen. Now this carbocation, if it is generated, that will be stabilized by this pi bond. So what will happen, this pi bond will be delocalized, and here half bond will form. So here methyl and here palladium will be there. So this charge is delocalized over this pi cloud. So this is the non-classical carbocation. Because you can see this double bond is quite far from this double bond or this carbocation. So you get this, and after addition now. So water will attack here. So after beta hydride, so this is the hydride. Beta hydride elimination, you will get the aldehyde. So another question was asked about mercuration, oxymercuration, demercuration, that with butyl. So what will happen here if we add mercury acetate? So here, that is the equatorial side, mercury will coordinate, and this is common. So if you do that, I will show in a minute that if you do bromination also, you will get this kind of intermediate. And now water will attack. So this is the axial attack always. So you get the trans diaxial orientation. In fact, so you get this one. Now I was telling the bromination. So if you add to bromine, what will happen? So this bromonium ion will form, and you know this Br minus. So this is the called the diaxial. So that 180 degree you can maintain between the reactant and the leaving group. Yes. So you get this one, the diaxial bromine. Maybe later it can flip to the cis, but this will be then trans. But the relative geometry will be like this. So this. So Honey is asking if there is multiple double bond in compound, then which olefin will react? Yeah, it depends on the structures of olefins, right? So there, you know this. If it is steric factor is there, that means the turbulent double bond will react. Okay, Madan Kumar is asking that the epoxidation is given axial side. This we have to check. This depends on conditions sometimes. Because if you do at high temperature, then there is a possibility of thermodynamics control product that we have to check. Because whatever I discussed so far, that is the kinetic control. Honey is asking migratory aptitude in diene-phenone reaction and actually this is not in our syllabus, but you search online, you can get other videos, okay, from other sources, or you can search book also. Yes, so regarding assignment, our TA will check and they will coordinate if you have any problem. So if you have any question, you can ask. Otherwise, we will conclude. Okay. Okay. Thank you.